Gold. This is what the alchemist's dreams were made of. The medieval thinkers spent their lives trying to find a way to turn cheap metals, such as this lead, into gold. Success would bring them fame and infinite fortune, but is such magic even possible? Join us in the search for the Philosopher's Stone. The alchemists were obsessed with the idea of producing a philosopher's stone, a magical rock or powder that could turn metals into gold. There are even stories of espionage, kidnap, and even murder in a bid to steal the secret of the stone. But what about the gold I just made? Well, I'm afraid we cheated. I'm not an alchemist. My name is Dr. Peter Wathers, and I'm a chemist from the University of Cambridge. I did start with lead. Well, it was a specially prepared form of lead that reacts with the oxygen from the air to give this beautiful lead oxide, this yellowy orange compound here. So we did cheat here. And my philosopher's stone, well, it was just a hot coal which started this reaction. So some alchemists use this reaction to try to convince people that they could make gold. But is such a feat even possible? In the last of this year's Royal Institution Christmas lectures, I hope to find out. In the previous lectures, we've looked at the elements in the air and in water, and now we're going to look at the elements in the earth and how we can extract them, how we can use them, and whether we can turn one into another. To help me, I have a giant periodic table made up of members from the audience here at the Royal Institution. Okay, so let's just have a look at the elements that we've already talked about. We have lead. Can you stand up, please? Lead. Thank you. So we were looking at you, and you were reacting with the oxygen from the air. Can you stand up, please, oxygen? Okay. And now this is how we normally find our metals in the earth. We don't find them lying around. They're normally combined with the oxygen from the air, or maybe sulfur, or occasionally other metals. Thank you very much. And if we have our periodic tables down now, please. But occasionally, we can find metals just lying around, and the classic case is gold. Where are you, gold? Now, you are so special because sometimes you can be found just lying around. In fact, here's a piece of you here. This is a gold nugget. Thank you, periodic table, at ease. So this is pure gold, and it can be found like this in nature. In fact, this is how it is normally found. Now, the remarkable thing about gold is it doesn't change over time. So you could leave it for tens, hundreds, even thousands of years, and it will still have this beautiful appearance. Now, I've got a very old piece of gold to show you now. Would you please welcome, from the Museum of London, Muriel Jeter. Now, I gather that this is a piece of sort of local gold, is that right?
Exactly, yes. It was found in London, in Cannon Street, in 1976, and it's actually a Roman gold and emerald necklace.
That's beautiful. So this is pure gold wire running through these
That's
emeralds,
right,
yes? Uh-huh. And you say this is from the sort of early Roman time. This is how old? About 2,000?
Nearly 2,000 years old, yes.
2,000 years old. But, I mean, has this been heavily restored, or is...
Been given a bit of a clean to get the mud off. But
just the mud off, and the gold
yes.
itself was looking just like this.
Exactly, that's why it's so wonderful for archaeologists.
Exactly. I mean, for me as a chemist, I think this is incredible that you can find gold just in this state, and it doesn't tarnish over time. It doesn't combine with oxygen or water or anything. This is how you find it. You can see that clearly it was highly prized, and I think maybe you should take it back to the museum then. Thank you very much. A big round of applause, please. So this has lasted so well because, I mean, it was so highly prized, so valued there, but also because it didn't change over time. But of course, you know, we have a saying about the value of gold. Sometimes people are told, you know, you're worth your weight in gold. Have you ever been told you're worth your weight in gold?
Yes.
Oh, you have? Oh, good. Who told you that then?
I can't remember.
Can't remember, but yeah, probably your parents, yes. Maybe we should ask gold. So where's gold sitting? Are you gold? Yes? Okay, have you been told that you're worth your weight in gold before? They've told you this, have they? Well, I think we should see just how much gold that would be. Would you like to come down to the front, please? And would you like to face the front here? Now, would you like to tell everyone your name?
Emma.
Well, would you like to take a seat on here? If you just carefully sit down on this. That's beautiful, lovely job. Okay, right. You sitting comfortably?
Yep.
Then we'll begin. This is where I get very excited. This is all real gold. And it's pretty good stuff, actually. Have you ever heard of a big block of gold before? No? Well, have a feel of this. That is pretty exciting, isn't it? Don't you think? Would you like to feel this as well? I'm afraid I can't let everybody have a... I know, it's amazing, isn't it? And this is actually... It's about the same as 6 large bottles of fizzy pop. Now, I'm just going to put this on here. OK, I think you need more than that. Well, let's keep going. And let's put this one on. It really is pretty good stuff, this. Oh, this is 24 carat pure gold. And this one here. More still. Oh, not quite. No. OK, well, let's try this one. I think it's almost level, but not quite. I think we need just a little bit more. Has anyone else in the audience got any gold? Is there?
Well, I found some on the way.
Oh, you've got some. Oh, isn't that Nobel Prize-winning chemist Professor Sir Harry Kroto? I think it is. So what exactly... I think I might know what this is, but is this really your Nobel Prize?
Yes, they give them away.
They just give them away. But this is solid gold, isn't it?
It's solid gold.
It's solid gold. I think it's...
And I want it back.
Oh, well, of course, Harry, yes.
I trust you.
Oh, thank you. Yes, right. Right, anyway, maybe this is just what we need. So let's just try that on there. Oh, I think that's pretty well balanced now. I think that's quite amazing. I think this is 43 kilos of gold and 1 Nobel Prize. So thank you very much. It's a big round of applause. Just stay where you are for the moment. Well, thank you, Professor Kroto, for saving the day there. Now, this is quite amazing. So 43 kilos, but it doesn't actually look too much there, does it, Emma? What do you think? It's not. It's quite, as you say, it's very dense, and this is why it doesn't actually take up much space. If you were made of gold, you would weigh 800 kilos, which is about as much as a small car, which is quite a lot, really, isn't it? So that's pretty impressive. But how much do you think this is worth? How much do you think? Have a guess. Maybe we need some
quite
help
a lot.
I think you're right there. It's actually, yeah, quite a lot. Yes. Anyone have any other ideas from the audience? Anyone shout it out? Yes. 1 million. Actually, you're not far off, but it is even more than that. This is about 1.5 million pounds worth of gold just sitting here, which is pretty impressive, isn't it? Okay. So, right then, now, if you just stay where you're sitting, please, I need to unload this first of all. So I'll just take that and... So, just going to put these over here. There's a few little bits left. And there we are. That's fantastic. Okay, thank you very much, Emma. Big round of applause. So, gold really is incredibly dense substance there. But actually, it's not the densest element. So can we just have cards up for a second, please? That honour goes to osmium. You are the densest thing in the universe. Well, at least on Earth. Did you know that? No, I don't mean that in a bad way. This is just you as an element. Osmium is incredibly dense indeed. Okay, now can we just keep, so cards up for the same people in the same row as osmium and gold, everyone else down. So cesium stay up, barium stay up, I say all the way over to mercury. Now why is it then that these elements here are so incredibly dense? The most dense element is osmium, closely followed by iridium. Well, atoms after osmium, iridium, gold, all these other ones are getting heavier, so the atoms themselves are heavier, and yet these ones are most tightly packed. So it's not just to do with how heavy the atoms are, we also need to look at the bonding that we have between them. And this is what we can see in the graph here. This shows how much energy we need to put in to separate a certain number of atoms of these elements here. And we see that we've got a peak around tungsten, and this is why we use tungsten in light bulb filaments, because it's very difficult for you to pull them apart, and we have very high temperatures. But as we go beyond tungsten, the bonding isn't quite so strong, but the atoms are getting heavier, and so it's a bit of a balance between the strength of the bonds, how tightly they're packed, and how heavy the atoms are. And this is why we reach a maximum for osmium and for iridium. Gold and so on, platinum, still very dense, so they're still very dense afterwards, but the maximum is there for osmium and iridium. So, osmium is even more expensive than gold, in fact. And if somebody was really going to pay you a compliment, they would say, you're worth your weight in osmium. Okay, but actually, these metals are not the only precious things that we can extract from the Earth. There are even non-metals that we can sometimes find as well. Hello. Hello, Professor Croteau. I'm assuming you would like your Nobel Prize back then, would you?
Well, I'd swap it for those bigger ones. But
yes, yes. I think so would I, yes. But, well, there we go. Thank you very much. But actually, perhaps you could tell us what you won the Nobel Prize for then, please.
Well, it's for discovering an alternative to these. This is graphite and this is diamond. These are structures.
I mean, these are actually the only ones that I knew about when I was at school. So in the textbooks, they were just two types of carbon, two different forms called allotropes. One has this arrangement, and this one is the graphite. This is the sort of thing that you find in your pencils. It's pretty soft and, well, carbon. It's just an arrangement of carbon. Diamond looks very different, though, doesn't it? I don't suppose, by the way, I mean, you very kindly lent us your gold, but I don't suppose you have a spare diamond on you, do you?
Well, I don't myself, but my wife actually has one.
Aha!
Right. You don't want to take that as well, do you?
Well, it's all right. It's all right. Okay, thank you.
Hope I get it back.
Thank you, Mrs. Croteau. Of course, yes, you can trust me. All right. Okay, this is a beautiful ring here. It's sort of an engagement ring or something. It's really quite lovely. It's, the diamond comes out quite easily, doesn't it? Yes. But we can see it more clearly now, though, so can't we? Look at that. This is beautiful. What a beautiful diamond. So it is a real diamond, though, is it?
It's as real as you can get.
Oh, it's quite stunning. So, but, of course, we want to show that this graphite is made up of carbon. And there's one way we can do this. We can burn our carbon in oxygen, and we'll get... What will we get?
Carbon dioxide.
Carbon dioxide, see, it's pretty good. Yep, carbon dioxide, yes. And then if we bubble that through lime water...
Oh, calcium carbonate.
Calcium carbonate. That's the test for carbon dioxide, of course. And it'll be what? Oh, I didn't ask you that one. Yeah,
no,
just getting carried away now. Right. Okay. Anyway, let's just see this over here. So we have some apparatus, and this is where we're going to burn some graphite, all right, and show that it is made of carbon. So what's bubbling through here is just oxygen. This won't react with our lime water at all. Okay, and we're going to see if we can light the graphite and get it burning inside the oxygen. And, there we are. Thank you. That's great. So now we have a hydrogen flame. So this won't produce anything. It's only going to produce water. And you can see the water just beginning to condense. Beautiful. I'm going to turn the flame off. Look at that. What do you think?
It's brilliant.
I think it is literally brilliant, yes. This is the carbon combining with the oxygen that's flowing through here, and hopefully we're going to see this changing colour, giving us the milky colour. Yeah, showing that there's carbon dioxide present. I mean, I think we should test diamond as well, don't you? What do you think? Yes? Does Mrs. Croteau mind?
Okay.
Okay, in the name of science. Well, that's very kind of you. Harry seems a little nervous. Well, sure it is a real diamond,
well, I think it's real diamond, yes, I'm sure.
Well, actually, let's give it a go then. So we'll just put it on there. And again, we'll put this on here. Right. So we have our flame. Here we go. the moment of truth. Now, can we get our diamond to burn in the oxygen? I think that. Ah, look at that.
I hope you can afford to pay for this.
Well, the good news is, Harry, it is a real diamond. Okay? I think this is absolutely stunning. I mean, that diamond there is, it is burning in oxygen. It's combining with the oxygen of the air. Have you ever seen a diamond burning like that before?
No, I haven't.
No, it is quite stunning to see,
right.
isn't it? And remember, there are no flames coming from this. So this is just, again, the heat of the reaction as the carbon combines with the oxygen that's present flowing through here, forming carbon dioxide. Oh, that is absolutely stunning. Just look at that. It's glowing all by itself. It's absolutely brilliant. I think that's amazing. And look, our lime water is going milky.
It's the most expensive lime water I've ever seen.
Actually, I think you're probably right there. It really is the most expensive lime water that you've ever seen. But, well, actually, while we're waiting for your diamond just to
disappear,
to disappear, yes, maybe you could tell us about your Nobel Prize again. So I think it has something to do with this.
I think it does, yes. It's.
Would you like to come round to the front,
sure.
actually? We'll compare it to these ones. So this one was the graphite. This
Last diamond, yeah.
is the diamond.
And this is the third form, well-characterized form. And it consists of 60 carbon atoms in the shape of a soccer ball. And it was such a fantastic surprise when we discovered it. And one of the clues to its structure was Buckminster Fuller's geodesic domes at Montreal. We had visited that, and I remembered it. It was in a book of mine. And when we were trying to work out how a sheet of graphite like this, or a graphene sheet, might close up, what we discovered is it could close up if it had 12 pentagons. You cannot close a sheet of hexagons up. It won't close up. But if you have 12 pentagons, it will, and you're all familiar with that in the case of the normal soccer ball with 12 pentagons, black pentagons, and 20 hexagons. And that's the magic that Buckminster Fuller knew, and other people as well. And I called it Buckminster Fullerene because there are double bonds as there are in benzene. So the ene ending was just a beautiful sort of ending to a great name.
So since my time at school then, the textbooks have to be rewritten with a new form of carbon discovered by this chap here. I think that's quite
And colleagues
remarkable.
in the States, okay.
And your co-workers in the States.
Okay.
We should have another look at your diamond here. It seems to have decreased in size. But I think we should come clean. Don't worry, we didn't destroy Mrs. Croto's engagement ring. I mean, that really would be quite harsh. This it's a pretty low-grade diamond. It still looks pretty good to the naked eye, but actually the experts say it's not very valuable at all. But it is a real diamond, and it is combining with the oxygen here, and I think that's a pretty stunning reaction. So thank you, Professor Croto, for coming in. It's a real privilege to have a Nobel Prize winner here helping out with an experiment. Thank you very much. Thank you. So, is it possible, though, that we could take this worthless carbon dioxide and get our diamond back from that? I mean, that really would be the alchemist's dream, recovering something precious from something worthless. And, well, got a demonstration here that shows that this may be possible. I'll just turn this round. Okay. Now, this tank is filled with carbon dioxide gas. We've put some solid carbon dioxide in the bottom, which is just slowly evaporating, turning into the gas here. Now, we can't see the gas because, of course, it's colourless, but it is there. Now, how can we test for this? Does anyone know another use of carbon dioxide? Yes? To put out flames, yes, exactly. So I wonder if we have a flame, please. Is there a flame anywhere? Ah, yes. Well, here's a flame that certainly needs putting out. So if I just lower this into the tank, there we are, you can see that it goes out. And this is because, of course, the tank is filled with carbon dioxide, and carbon dioxide doesn't support combustion. Right, now then. But we've also placed in this tank some magnesium metal. And I'm just going to fish this out. So this is a little nest of magnesium metal. So I'm going to light the magnesium here, and it burns with a brilliant white flame. There we are. And now I'm going to lower this into the carbon dioxide, and it seems to be burning even more vigorously now. Now, the flame is still burning, but what about this? This one, well, this one still goes out. So our petrol is extinguished in the carbon dioxide, but the magnesium is reacting with it. The magnesium is stealing the oxygen away from the carbon dioxide, and, well, we'll have a look at what we've got at the bottom. But let me take this out. So you can see magnesium oxide covered over what was the magnesium here. But look in the centre. What we've now got is black carbon. So the magnesium removes the oxygen, leaving behind the carbon from the carbon dioxide. So we can get our carbon back from the carbon dioxide, but, well, it's not a diamond yet. Is it possible to turn that carbon into a diamond? Well, actually, this is what happens deep within the Earth. And this is a diamond in a rock, just as it would have come out of the Earth. This is really quite beautiful indeed. So deep within the Earth, the carbon is heated up and compressed with huge temperatures, huge pressures, and the carbon that we saw there, the black carbon, is converted into diamond. Now, recently, chemists have learnt how to copy this process, how to turn graphite or other forms of carbon into diamond. And I'd like a volunteer to help me out with this one, please. Yeah, in the checkered shirt. That's lovely. Would you like to come down to the front, please? OK, would you like to come down to the front? Right, now, your name is?
Lewis.
Lewis, OK. Now, this is a diamond. Would you like to just hold this? What do you think? Are you impressed?
Yeah.
Yeah, looks like a piece of glass, though, doesn't it?
Yeah.
But it actually really is, it's a diamond. And this is a synthetically grown diamond. And this has been prepared, well, not from the high-temperature, high-pressure system that we can also use. This is a technique called chemical vapor deposition, where the diamond is gradually built up layer at a time. Now, I'd like you to take this, well, not keep it, but take it over here, bring it over here, and just sort of see, just place it on top of, this is a crystal, this is some ice here. Just note, hold it like this, that's it, like that. And then just put that on top of there and just sort of push through this ice. Now, how does that feel?
Cold.
Cold. It feels very cold. And what's happening?
Water's coming off as well.
I mean, this is ice. This is solid ice, and it seems to be going. You've chopped all the way through this quite cleanly there. So, as you say, it's got very cold. Yeah. Do you know why it's got cold there?
No idea.
It's used your energy to heat up this block of ice. So, yes, you're getting cold because it's taken the energy from your fingers here. So let's just try this again. If I just put this on here, it actually just it slices through like butter. It's really quite amazing. It just feels very strange, doesn't it? And I'm not sawing. It's not cutting because it's hard. It's cutting because it's a very good conductor of heat. Quite remarkable. So cleanly through this block of ice. Feels very strange, doesn't it? OK, well, thank you very much. Thank you for that demonstration. So that remarkable property of diamond was because it's an incredible conductor of heat. Now, to demonstrate this, to explain why this is so, I'd like some other volunteers, please. I'd like 6 people. So if we have, in fact, all of you, 6 of you, if you could come down to the front, please. So in a row, facing the audience. OK, keep going. In a row, in a line. OK, sit next to each other. Now, I'd like all of you to face that direction, please. So turn around, face that way. And just close up a little bit, just a little bit more friendlier than this. Just move up, just come this way a little bit, please. That's lovely job. Yep. Now just close up there and put your hands on the shoulders of the person in front. So face that way. Look, that's good. OK, very good. Now, at the moment, these are all pretty weak bonds between here. And watch what happens when I give a bit of energy this way. Just sort of don't do anything, just behave normally. So, Lucy, can you feel anything? But it was very difficult to get this energy through there, and this is because of all these weak bonds. Now, what I'd like you to do is just spread yourselves out a little bit more and hold arms with very rigid arms here. So you just need to spread, maybe work, I don't know, rigid, straight arms, that's it, rigid, straight arms, good. And now I'm just going to do the same thing again, just give you a jolt that end, and now you can see that you're certainly moving, yes? OK, so thank you very much indeed. Thank you for all your help there. Thank you. So this is why our diamond is such a good conductor of thermal energy. It's because the bonds are so strong holding these carbon atoms together, they're so rigid that this energy is very easily transmitted through. In fact, diamond is the best conductor of heat of any substance known, until very recently when scientists discovered a new form of carbon, another form called graphene, which is a single sheet of graphite. So that is an even better conductor of heat, but they're the best ones known. Now, so we've seen then that we can convert charcoal, we convert graphite into diamond under very high pressures or using the other technique of chemical vapor deposition. Surely if the alchemists had focused on that, they would have changed their attention away from trying to turn base metals into gold. But, of course, they were focused on metals because metals were incredibly important and still are very important. But it's only gold that has this unique property that we can find it lying around. Most metals we find in their ores. Ores like this here. This is the natural mineral. Does anyone know what it is? Anyone know what this one? Yes? It is an iron ore. Does anyone know what the name of the iron ore would be? Yes? Very good. Yeah, you're doing well. Hematite it is. Yeah, this is the mineral hematite. And this is now our source for iron, but it's locked up with the iron combined with oxygen. So somehow we have to learn how to extract the metal out of this. After all, it doesn't just fall from the skies. But remarkably, sometimes it does just fall from the skies. And this is what we have here. This is actually very heavy as well. This is a lump of iron that did fall from the skies about 5,000 years ago, and it landed in Australia. But look at this. What I wanted to show you here was the comparison between these two pieces. We can see that this is it's developing this sort of reddish-brown colour, the same as the hematite. So this contains iron. It is a slice of iron, but it's gradually combining with oxygen to form this mineral hematite. And we can show that it is a meteorite if we were to take a slice through this. And if we took a slice through this, what we would see is something like this. Okay, this is a slice through a meteorite, and it's really quite beautiful. So this has been cut, and we can see the side here. This is the outer surface of the meteorite, and here it's been cut with this incredible pattern here. This pattern is due to, it's been etched with acid, and it etches away certain types of the minerals that are in here, the forms of the iron. It etches away certain of them, and it reveals this beautiful crystal structure. And this proves that it's a meteorite, because it's impossible to get this pattern here on Earth. And that's because we need to cool down molten iron with a little bit of nickel in. We need to cool it down over such a slow rate, just 1 degree over thousands of years, if we wanted to see these crystals develop. So this really is quite stunning indeed. But over time then, the metal will gradually, this beautiful meteorite will turn into this ore here. Now, we can't wait thousands of years to see that, but we can speed this process up, and we can show how iron combines with the oxygen to form iron oxide. And I'd like a volunteer for this one, please. I'll have someone from this side. Where should we have? Yes, right on the end here. Would you like to come down to the front, please? Okay. And would you like to tell us your name, please?
Rose.
Rose, okay. Now, we have some iron over here. This is just iron wool. It's the sort of thing that you would like to feel this? It's just the sort of thing that you would use to sort of clean your pots and pans if you're helping out at home. Now, I'm just going to put on my goggles. And, right, we're going to combine this with some oxygen. So we want to see how much this weighs by itself. So this weighs 15.9 grams, okay? Now, the question is, what will happen when this combines with the oxygen from the air? How do you think its mass will change? Think we'll go up, we'll go down, we'll stay the same? What do you think when it burns?
It'll go up.
It'll go up, and why is that?
Because it will become more dense.
Okay, because it will become more dense. Well, let's have a look and see, shall we? I'm just going to apply a light here. This beautiful reaction is the iron combining with the oxygen, and look, what's happened to the mass? It's gone down. It's gone down. It's getting lower. Minus 0.16. So whoever said it goes down, you're quite right. But look, now what's happening? It's going up again. It is getting heavier, so whoever said it goes up, you're quite right. So everyone's right. So that's good. Now, why did it go down? Well, it went down initially because the wool, this iron wool, is treated with oil just to try and stop it combining with the oxygen from the air. Okay? But once this reaction has started, it is combining with the oxygen, and that's why it's getting heavier. So you are quite right. It is getting heavier, and that's because the iron is forming iron oxide. Thank you very much indeed. Thank you. So iron is pretty reactive stuff. It reacts with oxygen, and this is how we would normally find our metal, combined with oxygen. But what about if you couldn't extract the iron from this? What about before we knew how to do this? Well, the only iron that we would have had would have been iron from a natural source, such as this meteorite. And this sort of iron was used to make tools and so on. And I think we have an example of a tool using some natural iron here. Would you please welcome Dr. Caroline Smith from the Natural History Museum. Okay, this is really beautiful. So what exactly is this, though?
Well, this is an Inuit knife, and it's made of walrus tusk, so walrus ivory. But in the end, you can hopefully see that actually it has a iron blade.
So when this was discovered, I mean, the Inuits hadn't yet learnt how to make iron, how to extract it from the ores.
No, that's right. So they had to have a source of metallic iron. And at the time, it was thought that the iron in this knife was actually from a meteorite called the Cape York meteorite, which is a very large meteorite which was found in Greenland. And this knife actually came from Greenland. But we're not actually sure that's right now. We think it might be from somewhere else.
So I gather then that you've performed an analysis on this, and more recent research at the museum suggests that, well, you're beginning to question whether this is a meteorite, but it has to be naturally occurring because they didn't have the technology.
Iron. Exactly. They didn't have the technology to extract iron from things like hematites. They had to have a source of native iron, of metallic iron. And we think now that maybe this is actually from a place called Disco Island, which is an island off the west coast of Greenland, and it's one of the very few locations on Earth where you get metallic iron existing in metallic form.
Wow. And you've very kindly brought a couple of samples for us from, these are from Disco Island, aren't they?
These are from Disco Island, yep.
Okay. And they look quite different, but this one clearly looks very metallic. So we can see this here. It's got a sort of quite a shine to it.
It's quite a heavy specimen.
It is very heavy, yes. So this does look like a piece of iron. But this is naturally occurring iron.
This is naturally occurring iron that's found at the surface of the Earth. And in fact, tons of this iron has been found.
But why hasn't this one then corroded into the hematite?
Well, what we think happened is that about 55 million years ago, lava was erupted in this place, in Disco Island. And as the lava was coming up, as it was being erupted, it went through sedimentary rocks that have got a lot of carbon in. And the lava picked the carbon up, and you've got a chemical reaction happening where the iron, which was bonded with oxygen, just like here in the hematite, actually became metallic iron. It reduced the iron from the lava.
And we can see this is also a sample of iron, so this is iron.
Well, this is a sample of lava from Disco Island, so there is some metal in there, but not as obviously big as that.
But this one looks sort of, there's a very grey colour, and that's due to the graphite
that's
and
right,
carbon
there's graphite,
in here.
so we can actually still
see. We can see a bit of a smudge on here, on the paper. There's a black smear there. So that's just from the carbon that's present in here, the graphite.
That's right, that's right.
So actually, we've got a clip of a blast furnace to show. So this is how iron is now manufactured, and this is using carbon to steal away the oxygen from the iron ore, from the hematite. This is how we're producing iron. But what you're saying is then that nature beat us to it.
Nature's beat us to it about 55 million years ago, exactly.
That is quite amazing. So thank you very much for bringing these samples on. Thank you very much. Now, I really wanted to produce some molten iron for you here in the lecture theatre, but clearly we couldn't bring in a blast furnace, so we had to think of another way to do this. Now, we can learn from what we did earlier, actually. Remember when we used the magnesium metal to steal the oxygen away from the carbon dioxide? Well, we can do the same thing now with our iron oxide. We can use a more reactive metal, and we're going to use the metal aluminium. And you may be wondering why there's a safe under here. And, well, this is because, well, we have a bit of an embarrassing story here. We accidentally locked Andy's Christmas bonus in the safe.
Yep.
And, well, we tried getting into this safe, and it's a pretty hard thing. It's made of, this is pretty solid stuff, isn't it?
Yep.
And we can't really get into this, but the energy generated as the oxygen is taken away by the aluminium to form iron should be enough to get in here. So actually, can we just have a little look in here? Could you get the camera right in, please, just to show what's inside this vessel. So this is made of a very tough form of carbon, so this is made of graphite, and you may be able to see the sort of orangey colour. So that's our iron oxide. It's mixed with aluminium powder, and there's, well, the thing that you see sticking out there is a little bit of magnesium that I'm going to use to start this reaction. So hopefully we should generate some iron and see if we can get through into the safe. Sounds like a good idea, doesn't it?
If it's the only way to do it, then well,
there we go. Right, now I think we will need a safety screen around this, though. And I'm going to need a glove as well, I think. And Liza, thank you very much. Feeling confident?
Yeah, I can't see what could go wrong.
Yeah, what could possibly go wrong? Exactly. Now then, let's give it a go. So, you'll see a bright white light first of all. That's just the magnesium that we saw earlier. That's the magnesium combining with the oxygen from the air. OK. And we should know when it starts. I think it started now. So this is our little blast furnace here. Oh, look at that. Fantastic. We've got some molten metal there. Can we lose the safety screen now, do you think? I think that would be good, if we can possibly take this off. Yeah, lovely job. Right off the top, very carefully. And I'm just going to see if we can... Can I give you that?
Yep.
Thank you. And see if we can pick up this. What have we got here? Ah, yes. That's wonderful. Look at this. So it releases such an enormous amount of energy as the aluminium combines with the oxygen from the iron oxide. And good news, Andy, well, I think good news and bad news. The good news is there's a hole in the top of the safe, but the bad news is there's a lot of smoke coming from outside.
Oh, and I think I've just found the key as well.
And now he finds the key. So at least we got into the safe. Well done. So thank you very much for that. Well, we formed there, during that reaction, aluminium oxide. Okay, as the aluminium took the oxygen away. And this is how we find aluminium in nature. We find it as aluminium oxide, and here's a sample here. Let's go over this side. So would you like to... what do you think to that? Yeah. It is light, and this is because it's a very light metal aluminium. But how can we get our aluminium out of this rock? And this, for a long time, was a great problem. And it was only solved when chemists realised they could use an even more reactive metal, and this was the metal over here, the metal potassium. But when this was first discovered, it was a bit of a curiosity. There was this amazing substance, aluminium, and it did have very remarkable properties. And actually, I need another volunteer from the audience. We'll have someone on this side. In the green, would you like to come down? Yes, please. And your name is?
Ailish.
Sorry?
Ailish.
Ailish. OK, great. So, now, obviously you've seen a lot of aluminium before, haven't you? Yeah. Because it's very cheap now, because now we have worked out how to extract it from the ores. But initially, I say, it was incredibly difficult, and that made it incredibly expensive. And, in fact, so valuable and so strange that this chap, this is Napoleon III, he had a whole cutlery set made from aluminium. And I think we have some aluminium utensils here, so you have a look at these. What do you think?
Very light.
They are very light, aren't they? So this was the remarkable thing. So, in fact, with Napoleon's cutlery set, he had his cutlery, and it was so valuable that if he had a huge feast, he would give his most honoured guests the aluminium cutlery, and all the rest just had to make do with gold. Okay? It seems strange to us now, because we do know how to extract aluminium, and it is incredibly abundant, and we can find loads of it around, but it was very difficult to get it out. So, just to say, it does feel very light indeed, doesn't it? That is one of the remarkable properties. But it isn't actually the lightest metal that's known. Do you know what the lightest metal is? Look over there.
Lithium.
Oh, yes, you're quite right. It is lithium. It's lithium. Give us a wave, lithium. Lithium is, in fact, a metal, and it is incredibly light. Now then, we have made the world's first lithium spoon, which is very exciting. And here it is. This is our special RI spoon. And isn't that beautiful? Would you like to feel this?
It's really light.
It really is. It's amazingly light, isn't it? Don't you think? It feels almost like plastic or something. But it is solid. That is solid metal. But it is quite remarkable, isn't it? Don't you think?
Yeah.
So this is just... this is my dinner, I think. This is some soup. And, of course, cutlery sinks in it. But would you add the, just drop it in, just throw it in and step back. And look at that. It's, well, first of all, it is incredibly light and it's floating on the surface, but it's also reacting. I'm going to fish that out. So it's very reactive indeed. I don't think lithium spoons are going to catch on at all, do you? And because it's just too reactive.
Explosive.
Exactly, too explosive. Thank you very much indeed. Can we have a big round of applause? Thank you. There's a bit of coughing there, just from some of the reaction there as the lithium combines with the oxygen, as it's reacting with the water vapour. Yes, thank you. So the lithium there, it floats on the surface, it is incredibly light, but it's incredibly reactive as well. I mean, that may be the world's first lithium spoon, but I think it's safe to say it's also going to be the world's last. But it does show how reactive lithium is, and maybe we can use this element to prepare new elements, and we can indeed. So we have a reaction here to generate a new element from silicon dioxide. Now, does anyone know where we find silicon dioxide? Any ideas right at the back? In sand. You're quite right. We find silicon dioxide. It is sand. Now, we've got some lithium in here and some sand. Okay? So we've mixed the two together, little lithium pellets and some sand. And I'm going to heat this up in a moment and see what happens. So this is lithium with silicon dioxide, and the silicon dioxide is, of course, it's a mineral, it's just sand. Quartz, it's the same stuff, silicon dioxide. So sand is smashed up pieces of quartz. And I'm hoping that we should see a reaction take place. And there we are. So this is a very violent reaction again. And this is as the lithium is stealing the oxygen away from the silicon dioxide that makes up the sand. And, well, anyone have a guess at what we're going to make? Silicon. Very good. So we take the oxygen away from the silicon dioxide, and we end up with silicon. Remarkably, this is a single crystal of, well, very purified silicon. And it's very valuable and very precious, and I need to put on some special gloves for this. And it's hard, it's very solid, it's sort of like a metal, and it's incredibly heavy. Actually, I can hardly lift this thing up, but it's grown in this very special way here. I say this is one crystal of silicon. In fact, it has a seam running all the way along the top here. This just proves that it is, in fact, one crystal. And why do people grow these? Well, they grow them from the molten silicon. They would keep molten silicon, just keep purifying it, heating it, and allowing it to recool into this rather strange-looking shape. And they do this because they're trying to make these. And this is a silicon wafer. So it's just a sheet of silicon. It's just a slice from this. And these are used to make silicon chips. So this is where it's the same slice of silicon, and then they're sort of etching in and adding other dopants and so on, other reagents to this, gradually building up the silicon chips that we have in our mobile phones and in our computers. So a fantastic use for this element, silicon, the element that we extract from sand. So chemists are always finding new uses for their elements, even though this has been known for well over 100 years, a couple of 100 years. It's only relatively recently that we found out how to use this element to make silicon chips. So far in the lecture, then, we've swapped elements around to make different useful materials. We've stolen oxygen from iron oxide to make iron, and we've stolen it from sand. We've even rearranged the structures of carbon to turn graphite into diamond. But what we still haven't done is turn one element into another. That's what the alchemists were trying to do, to turn lead into gold. So is this possible? Can we turn one element into another? Well, yes. This is the process of radioactivity. And this occurs, well, deep in the earth and indeed all around us. Now, can we have our periodic table up, please? And those of you elements who are radioactive, I'd like you to stand up, please. So all the radioactive elements, if you're radioactive, that's all of this front row here. Yes, you're all radioactive. Bismuth, we're not really sure about you. You're a bit unknown. But actually, you're so radioactive, you're no longer who you thought you were. You better sit down again. So what does that mean? Why do you have to sit down again? It's because during radioactive decay, an element changes into another element. Okay, if we have cards down for a moment, please. Now remember, what makes an element unique is the heart of the atom itself. That's the number of protons that it has within it. So this represents what's inside an atom. This is its nucleus. And we'd have to count the number of the red spheres, these represent the protons, to work out what element this is. Well, in fact, this is the element uranium. But the thing about uranium is, it's unstable, and bits drop off. So the element, the nucleus here, just gets so large that it's very difficult for these things all to stay together. And yes, bits do drop off. And when they drop off, though, it's changed into a different element. Because remember, it's the number of the red protons that define an element. So if we lose 2, it's no longer who we thought it was to start off with. Now, can we find uranium in our periodic table? Where's uranium? OK, there we are. Would you like to stand up, please, uranium? OK, very good. So, uranium, you are radioactive. And bits do drop off. It's quite slowly, don't worry, so we won't notice. But actually, when it does happen, when a bit does fall off, well, you change into a different element and you move a couple of spaces along. You become thorium. So maybe you should move over to thorium. You better put your card down because you're not you anymore. Get it? No? OK. Anyway, so you're no longer you, you're actually thorium. You better move over. No, you better go over there. You're on thorium space now. But actually, both thorium and uranium have also decayed. And if you decay now, you're going to become the element radon. You're also radioactive, I'm afraid. So if you decay, you lose a couple of protons in an alpha particle. You're not radon anymore. You've become polonium. Now, can we see this, though, in action? Well, we can using this apparatus here. This is known as a cloud chamber. And the tank that we see here contains an atmosphere of alcohol vapor. And it's got a lot of vapor in there, and it's actually trying to form little droplets. And there's a temperature gradient. There's a little heating wire at the top, and it's cooled down from underneath. And so it's sort of gradually freezing out, and it wants to form droplets, but actually it's much better, it's much easier if there's something there to help it. And any charged particles can cause this. Now, all the tracks that you can see now, all these little wispy white trails, are actually particles of radiation. This is natural radiation, just in the air around us. Now, we don't tend to think of radioactivity as being sort of very natural, but of course we're all weakly radioactive because of some of the radioactive elements in us. And here we can see radiation in action here, just in the air around us. Now, I'm going to introduce into this a sample of a radioactive element called americium. Look at that. And you can see the tracks forming here. Each little track that we see is the result of a charged particle being emitted from the element americium, and the particles emitted are alpha particles, and the alpha particle is 2 protons, 2 neutrons, and actually that is the heart of an atom of helium. So what we're actually seeing here is the birth of helium atoms, which I think is quite remarkable. So I'll just put this away. So it is possible then to change one atom into another. Well, nature seems to do this, but can we? Well, actually it is possible, and one of the first people to generate lots of different atoms was this chap here, Glenn Seaborg. In fact, he even has an element named after him. Where's Seaborgium? There we are, right in the middle of the periodic table here, Seaborgium. So in 1980, Seaborg did an amazing experiment. He took bismuth and he turned it into gold. And this is what the alchemists had been dreaming of. He changed one element into gold. Okay? What he did was take bismuth. Can we just have our periodic table up for a second, please? So he took the element bismuth, and he fired atoms of carbon and neon at this, and it knocked out a number of protons until we ended up with gold. Okay. But unfortunately, he only ended up with a few thousand atoms, and this is not enough to get him rich. It was a very expensive experiment, took a lot of money to get this, and all he made was a few atoms. But it is possible to do it. So radioactivity is a natural process, but it can also be brought about by firing one atom at another and changing it and creating new, heavier elements, or even to make gold. But do we even want to make gold? Or are there other things that fascinated the alchemists which modern scientists have taken one step further? And this is another naturally occurring rock that has really quite remarkable properties. And this one amazed the early alchemists. And I'll show you why. I think over here, our audience members have some paper clips. Have you got some paper clips? Okay. And I'd just like you to put your paper clips onto here. Just put them onto the rock. That's it. Just they should stick by themselves. Now, it's not really a surprise to us because we've all seen magnets before. But just imagine if you were the first person to ever see a magnet. Now, I have a book here from the 1530s that describes this magnetic rock, this lodestone, and they really did find it quite remarkable. Okay, so this here shows this magnetic rock. This is the magnet here. There's a ship sailing past a mountain that's supposedly made of this lodestone, this magnetic ore, and, well, you can see here, these are the nails from the ship. They've supposedly been sucked out of the ship, so this is a sort of a warning that there's this incredibly strange magical material with these amazing properties that would suck the nails out of your ship and, well, you'd be shipwrecked. So there's a warning for you. Okay. Thank you. But nowadays, scientists have learnt how to make even stronger magnets from the elements. And if we just have our periodic tables up again, please. Some of the strongest magnets now made use the element neodymium. Do you give us a wave, neodymium? There you are, up there. Very good. So the strongest magnets in the world are made with neodymium. Now, this element was discovered in the 1880s, but it was over 100 years later that scientists learnt how to use this element to create these magnets. Okay, thank you very much, periodic table. And I have a couple of these magnets here, and they really are very strong indeed. So these are little neodymium magnets. Okay, so here, I would like to just pull these apart.
You can't. They're stuck together.
So, no, they're not stuck together. Try again. Yeah, I'll give them to your neighbour, see if he can do that then. What do you think? Can you pull those apart?
No.
I promise you they're not stuck together. I can probably slide them or something if I push. There we are. See, they're really not there. But look at that. They're very, very strong magnets indeed. So even though the element neodymium has been known for over 100 years, these magnets have only recently been developed. Now, these really are quite strong. And I think to show just how strong these are, I need another volunteer. And I think we should have one from this side. Yes, would you do it in the group? Yes, would you like to come down to the front, please? Okay. Very good. Now, so you're feeling strong? You are. That's good. Can you tell us your name then, please?
Marie.
Marie. Okay. We're just going to bring down this rig here. Now, we're going to suspend you from the ceiling using this little magnet here. So that's the only magnet. This is a block of iron. It's not magnetic. I can show that with a paperclip, just holding a paperclip. Oh, it stays on it, yes, but it's not attracted to it. This is our magnet. I'm not going to put the paperclip on this. I'd never get it off again. So if you'd like to come over here, please. Right, now I just need to very carefully put this in the middle. Oh, perfect. Right, and just clip this on as well. Okay, so clip that onto here. Right, okay, so you're feeling strong. Okay, right, if you just hold on to here. Okay, that's it. And can you just raise up the winch then, please? And hold on strong, hold on tightly. We'll just see if we can lift you off the ground. So you do need to hold on very tightly. Okay, you might need to move forwards just a little bit. Keep holding on, holding on. Now just watch the feet. Just keep holding on, holding on. There we are, look at that. You are now suspended from the ceiling. That was fantastic. Thank you very much. You'd like to go back to seat. So it really is pretty strong magnets there, okay? We can actually hang from them. I say it's just using the power of these new magnets. But these are incredibly useful, and they find uses, for instance, in turbines. They're also used in electric cars and so on as well. So these new materials, very, very useful. Now, but we can create even more amazing materials using the elements. Can we just have our periodic tables up for a moment? So we were using magnets there to suspend, and these were the neodymium magnets. But this, we're going to use some superconductors. And these superconductors are made from the elements yttrium. So yttrium is just here. Give us a wave, yttrium. There's yttrium. And from barium. So barium, give us a wave, barium. Very good. And copper. Okay, there's copper. And oxygen at the top there. So put you four elements together, and we get these amazing materials, high-temperature superconductors. This is called a Mobius strip. Okay, it's a rather strange-looking thing. How many sides has this got? Two? Yes, well, you'd think so. Well, actually, if you start here and you keep on going round, okay, you'll actually come back underneath. And then if you keep going round, you come back where you started from. It actually has one side, this mathematical shape, which is very unusual. And I can show this using our little superconductor in a moment. So this Mobius strip is covered with these neodymium magnets, these very, very strong magnets. And we've got a superconductor here. And this is the superconductor that's made from the barium, the yttrium, the copper, and the oxygen. This is the ceramic there. This is this disc in the center. And we're cooling it with liquid nitrogen in this little holding tray on the top. And it levitates quite nicely. And there we are. It's come back to where it was. And now it's actually hanging underneath this strip. But it needs to be cooled down, so we're cooling it with liquid nitrogen. That's in order to enable these superconductors to work. They only work at these very low temperatures. So eventually it's going to warm up and it will fall off the track, so you need to catch it when it does fall. See if, oh, you meant to catch it. No, I would, so just pass it to me straight away, please. Thank you. That's lovely. Okay, thank you very much. Thank you for all your help there. Catching it. That's great. Thank you. So, it's really quite remarkable properties then of this ceramic made out of the elements barium, yttrium, copper, and oxygen. So we've come a long way since the days of the alchemists, when the whole world could be made from air, water, earth, and fire. I hope you've enjoyed our quest to discover what's really making up the world around us. And if you remember one thing from these lectures, it's that the work of the chemist is not complete, that new combinations are being discovered all the time, and nobody knows what exciting properties they may have. Now, I'd like everyone to pick up your cards one last time, and have a look at your card. Just remember what element you've got, and I want you to go home and research about your element and think, what uses can we put this element to, and what new possibilities could there be? And so who knows, you may be able to solve some of the challenges of the future, and maybe even make something more valuable than gold. Thank you, and good night. Thank you.
Stay with us, there's a trip to Georgia coming up next, home to one of the world's most dangerous roads.